What's up guys, and welcome to this tutorial on question 1 of the 2019 final exam. Okay, like my normal recommendation, I suggest that you guys do the multiple choice question last, which is exactly what I've done in this video series as well. I've done all the long questions before going on to the multiple choice. Okay, the reason being is because sometimes the multiple choice can be deceiving and look easy, whereas normally there are some tricks in some questions. Okay, so let's go over this question. Okay, so question 1.1, which row shows a physical quantity and a correct unit? Okay, so let's go through all of these. Okay, so the units of force is kilograms meters per second squared, right? So obviously this is meters per second, so answer cannot be A. Okay, so remember force equals mass times acceleration. So a mass has units of kilograms, acceleration is meters per second squared. So that's how I worked that out. Okay, efficiency. Remember our efficiency is a dimensionless unit, so it has no units, so it cannot be B. Momentum, our equation for momentum is our mass times our velocity. Our mass is in kilograms, our velocity is in meters per second. So again, we don't have the right units here. And then work is joules, which is equal to a force times a displacement. Okay, work is equal to a force times a displacement. A force has units of newtons, and a displacement has units of meters. So we have our Newton meters. So our answer is question 1.1. The answer is D. Okay. So again, obviously, I've taken a bit of time to make sure that all the other options are incorrect, but if you looked at the units very quickly and you figured out that this is the correct answer, then it would have been simple. Okay. The graph shows, question 1.2, the graph shows how the velocity of an object changes with time. Okay, so we have a VT graph, and we want to see, they've given us which of the following shows the correct acceleration time graph. Okay, so remember our acceleration from a VT graph is we're looking for the gradient. Okay, so our gradient is our change in y over our change in x. Okay, and throughout this entire process, we can see that the gradient is constant, right? So obviously these two options are wrong immediately, because in this A and B, it's saying that the gradient is changing, which is not the case. The gradient is constant. And then if we calculate our change in y over change in x, it is going to be a positive gradient. Okay, so our gradient will be positive. In case D, the acceleration is negative here, so it can't be D, and the acceleration is positive here, and it's constant like we expect, so the answer is C. So question 1.2, the answer is C. Okay, question 1.3, an object initially at rest, travels a distance of d in a time t at a constant acceleration. What is the time taken for the object to travel 16d from rest at the same acceleration? Okay, so I'm going to break this into two scenarios. So let's work out the first scenario here. Okay, so hopefully you guys have identified that this is a classic UVATS question, UVATS. Okay, our initial velocity is from rest, so u equals 0. Our final is unknown, our acceleration is unknown as well. Okay, our time is t, and our displacement is d. Okay, so what we know for both parts of the question is we have the same acceleration. So basically, I want to solve for this acceleration here in the first part. So I can use the equation s is equal to ut plus a half at squared. So s is equal to d, this u is equal to 0, so that entire term goes to 0, is equal to a half at squared. So what I know is that d2d over a is going to be equal to my t1, right? So we know that, this is the acceleration is constant, and I'm going to label this t1. Okay, so now we know how long the object takes for the first scenario, and we have labeled that t1. So now we want to know the time taken for the second scenario, okay, where the distance is 16d. So very much a similar situation. We have u, v, a, t, s, and we know our acceleration for 1 is equal to our acceleration for 2. Okay, our initial is 0, our velocity is unknown, t is what we're looking for, and d, or our distance now, or displacement, is equal to 16d. So now we use the same formula. We can say that s equals ut plus a half at squared. That term goes to 0 once again. So what we have is 16d is equal to a half a, let's call this t2, t2 squared. Solving for t2, we have 32d over a square rooted is equal to t2. Okay, so now I have an expression for t1 and t2, but I want t2 in terms of t1. Okay, so what I basically want to do is pull out this expression from this expression right here. So how am I going to do that? I'm going to say this is 16 times 2d over a square rooted. Okay, so this part right here, let's do it in black, or let's do it in gray. This equation right there, or that expression right there, comes out here. So that's t1, right? So I can write this is equal to the square root of 16 times t1, because those two parts are exactly the same. And the square root of 16 is obviously 4 t1. So t2, which was that left-hand side, is equal to 4 t1. Is that a solution? Yeah, so B. Okay, so the answer to question 1.3 is B. Okay, question 1.4. Two blocks of weight 7 newtons and 3 newtons are attached to rope X as shown. We want the vertically, it's hanging at rest. The mass of the ropes are negligible. Calculate the tension. Okay, so what is the tension in X and Y? Okay, so this question, the first thing we're going to do is draw free body diagrams for both of these. So this is this box, let's name this box A, and this is B. Okay, so for A, what we're going to have is we're going to have tension of Y, and the mass of A, which is 7 newtons, or the weight 7 newtons, and what we're going to have here is the tension in X. Okay, then for B, what we're going to have is the force downwards, which is going to be 3 newtons, and the force upwards is Ty. Okay, and we know that it's at rest, so for this first one we can say that the sum of the forces in the upwards direction is equal to 0, so Ty minus 3 newtons is equal to 0, so Ty is equal to 3 newtons, so we know the tension in Y is equal to 3 newtons. We can do a similar thing for box B. We can say sum of the forces is equal to 0 because it's at rest. So what we have is Tx minus 3 newtons minus 7 newtons is equal to 0. So Tx is equal to 10 newtons. So Tx is equal to 10, so we have A or B, and Ty is equal to 3. So our answer is B. So question 1.4, the answer is B. Okay, so moving on, the mass of a rocket propelled car is approximately equal to the mass of the fuel in its tank. Okay, so we have a car with a rocket, okay, and it's the car and the rocket have got mass of the car, which is equal to mass of the rocket, so we have 2m. Okay, so what we have is that. So we have mass of the car and mass of the fuel, and that equals 2m because they're equal. Okay, the ignition, the rocket is ignited and the car is propelled in a straight line by a constant force. Okay, so F equals constant, and we can ignore air resistance, whatever. During the test, fuel is used at a constant rate. Okay, so the mass of the fuel must therefore be going downwards. Okay, which of the statements actually accurately describes the acceleration of the car during the run? Okay, so we're looking for the relation of acceleration. Okay, so initially what we have is that the force is equal to our mass of the system. Okay, so let's say mass of the fuel plus mass of the car times the acceleration. Okay, so that means we can say, and we know that F is a constant. Okay, so we can say that the mass of the fuel in the car times the acceleration is equal to a constant. So that means the acceleration is equal to a constant over the mass of the fuel plus the mass of the car. Okay, and so what we're basically saying in this equation is that the acceleration is proportional, right? It's proportional to my, or inversely proportional. So it's got a relationship where it's directly proportional to the constant over the mass of the fuel plus the car. So as, well, let's actually skip that. Let's just look at this part of the equation. As the mass of the fuel goes down, so the denominator goes down, right? And so when you're dividing a constant divided by a smaller number, okay, results in a higher acceleration. Okay, so as our fuel goes down, the denominator gets smaller, so what happens is our acceleration goes up. So basically what we can say is that as the fuel decreases, our acceleration will increase. So the acceleration of the car decreases, not correct. The acceleration of the car remains constant, not correct. The acceleration of the car increases as fuel is released, that is true. And the acceleration of the car is 0 as it's moving at a constant velocity. That is also not true because it's not moving at a constant velocity, it's experiencing a constant force. So our answer for 1.5 is C. Okay, so two cars of different mass m and m, small and capital, are connected to each other at rest. So the system is at rest. So velocity equals 0 there. A small explosion causes the car to move apart from each other after the explosion. The cart of mass m moves at the velocity v. The cart, okay, so the change in momentum of mass m is what? Okay, so we want basically the momentum of, or change in momentum of the big mass cart, right? So here we can use the conservation of linear momentum. So basically what we can say is that the momentum before the explosion is equal to the momentum after. Okay, so our momentum before is our mass times our velocity plus our mass times our velocity, okay, is equal to our, I'm going to use big M, or let's just say the momentum of the big mass plus my momentum, and we're going to take going to the right as being positive, my mass times my velocity. Okay, obviously the left hand side of this equation is 0, is equal to the momentum of the big mass plus mass times the velocity. So therefore the momentum of the big mass is equal to the minus small mass times the velocity. And this is equal to our change in momentum because we went from 0. Okay, so basically that should be our answer. So minus mv, small mv, which is correct. So 1.6, the answer is A. Okay, so moving on, two boxes, X and Y, both have the same mass, so they both have mass m. Box S is lifted through a vertical height h by a force F of magnitude F. Box Y is pulled up a slope by a force of the same magnitude, so the forces are the same to reach the same vertical height. Okay, so they both reach the same height. So a change in gravitational potential energy. Okay, so at this height up here, the EP is equal to the mass of the box, gravity times the height. Over here, it's EP is equal to the mass of the box, times gravity times height. Okay, this is box X and this is box Y, but we know this mass of X is equal to mass of Y, so that means these two equations are the same. So this is EP of X is equal to mass of Y, gravity, height, which is equal to EP of Y. Okay, so basically we can say that the change in potential energy is the same. Okay, so we can cancel those last two options. Okay, now we need to deal with the amount of work done. Okay, so the amount of work done, or work, is equal to our force times our distance, right? So the work for X is equal to the force, which is the same, times the distance, which is h. Okay, so h. It only has to go that height there. Whereas for the work done by box Y is equal to our force times this length right here. Okay, so what is that length? That length of it. Okay, if we know just some basic trick, this is our hypotenuse. Okay, so our hypotenuse is always going to be greater than any of their side heights. Is always greater than h. So we can say that the hypotenuse is always greater than h because of this right angle triangle. So it's going to be multiplied by the hypotenuse. Okay, so that means that the work of y is greater than the work of x, because the work of x is only equal to the same force times h. But we know that the hypotenuse is greater than h, therefore the work of y is greater than the work of x, is more for box y than for box x. So this option B. So the answer here would be B. So question 1.7, the answer is B. Okay, so the mass of a planet is twice that of Earth. Its radius is half that of the radius of the Earth. The gravitational field at the surface of the Earth is G, the gravitational field on the surface of the other planet. Okay, so once again, what we know is that we know our equation for the gravity on Earth is going to equal our gravitational constant times the mass of Earth over the radius of Earth squared. Okay, so let's say that's for Earth. The gravitational constant for the other planet is going to be equal to the gravitational constant times the mass is twice that of Earth, so 2 times the mass of the Earth, over, and its radius is half that of the radius of the Earth. So half times the radius of the Earth, remember, that's all squared. So if we solve this, what we're going to end up with is 2gme over 1/4r radius of the Earth squared, and this becomes 8 gravitational constant mass of the Earth over radius of the Earth squared. Okay, so now we have, this is our gravitational constant on Earth, which is that equation. These two are the same, so it's equal to 8 times the gravitational constant of the Earth. Is that an option? Yes, it is, option D. So question 1.8 is D. Okay, so a battery with negligible internal resistance is connected to a variable resistor X and a fixed resistor Y as shown in the circuit. The potential difference across the resistor X is Vx and across the resistor Y is Vy. Okay, so I'm going to say that overall it's got Vs. Okay, so that's the voltage of the, or Vc. Let's say Vc is the voltage of the cell. Okay, so from the get-go we can say that the voltage of the cell is equal to voltage of X plus voltage of Y. Okay, so as the resistance of resistor X is increased, what happens to Vx and Vy? Okay, so we're saying that the resistance of X goes up, right? So we know that that the voltage of X is equal to the current times the resistance of x. Okay, so if the resistance of x goes up, that would cause our voltage of x to go up. So Vx must increase. Okay, so Vx must increase, so we're left with C and D. Those are not options. Okay, so if Vx goes up, remember that the voltage of our circuit is constant. So if Vx goes up, then Vy must go down in order for it to remain a constant. So Vy goes down, so our answer is C. Question 1.9, the answer is C. Okay, and the last question is, a conducting square coil is placed in a uniform magnetic field. The magnetic field is directed into the page, and there's a clockwise current in the coil, which the arrow would indicate the direction of the force that acts on the side of the coil. Okay, so basically we have a magnetic field into the page and the current is going this way around clockwise. So this is a theory question, so the answer would be D. The force would be towards you. So question 1.10 is D. Okay, and that is the end of the paper. So I hope you guys found this useful, and yeah, thanks for watching. Cheers.